In this video, we're going to be working on binary models, or models that have a y variable that is equal to 0 or 1. And when we predict the 0 or 1, what we're trying to predict is the probability that the outcome is 1. And what I'll do in this video is spend most of my time on things that you haven't seen yet, and I'll skip quickly through things you've already seen. The new package we're going to use is the SQL-DF. This allows us in R to use the SQL language. If SQL is new to you, you can find SQL tutorials online, but I will spend a little bit of time talking through it here. I have two data sets here. One is similar to data that you've already seen. This bankruptcy data is annual financial information, so you've seen something like that before. The other is this bankruptcy data set, and it provides observations where bankruptcies actually occurred. So when we read this in, then we can look at the data. So when you look at this, it looks like data you've already seen. There's the firm identifier, the year, the end of the fiscal year, and these other items here that are going to allow you to calculate some variables related to bankruptcy and how liquid the company's assets are. Then in the other data set, we have this company key here. This is the identifier that's provided by the SEC, so this is their CIK code, and I've already merged that onto another identifier that we already have. This is the beginning of the bankruptcy date. This is the end of the bankruptcy date. So for example, Agway here went into bankruptcy in 2002, came out of bankruptcy in 2013. And so we have any companies that had a bankruptcy are in here. And over here we have the firm identifier, and then this Y bank is the thing we're going to be interested in, and they're all 1 in this data set, and the 1 means yes, the firm did go bankrupt. So there's our data set. What we want to be able to do then is combine the financial data that we have with the bankruptcy data, because we want to predict whether companies go bankrupt or the probability that a company is going to go bankrupt. So this is where we're going to introduce the SQL language. So SQL-DF is the package and also the function. And the reason we're going to go with the SQL language is it allows us some flexibility when we're combining data sets. So we're going to do what is called a left join here, and that means take all of the observations from temp and join bank wherever temp meets certain conditions. And so there are other types of joins. The one I use most commonly in this type of data is left join, but we could do other ones, inner joins, outer joins, right joins, but that isn't really that important right now. So the easiest way to get a handle on what this is doing is to do it and then look at the data. So there are certain statements that come in with a SQL language. So here select means choose columns. So when you're selecting columns, you're selecting from 2 data sets, and we have here the temp data set and the bank data set. And here I'm saying select from A, so I have little shortcut aliases for the data set. So here A is referring to temp, B is referring to bank. That allows us to do things in here instead of using the full data frame name. And by the way, SQL-DF means do SQL with data frames. Okay, so then the star means all columns, so A dot star means all of the columns from this temp data frame. Then we're going to take this Y bank variable. Remember, in the bank data, the bankruptcy data set, it's all 1s. So we're going to take that Y bank column, and that's the only column we're going to take from this bank data frame. So then that's easy to set up, right? So we always start with the select which columns are going to be in here. In the SQL language, you would start with creating a table. Here we're creating a table over here. So we're creating an object temp2 that is the result of this SQL statement. So that's the difference. If you went to another form of SQL language here, you would have something that says create a certain table. So for example, if you're going to use it in a different framework, you would have something like this to start out, and then you would go into selecting and joining. But here, since we're creating this object in this way, then that isn't in the SQL DF framework. So it says take this data frame, join on this data frame, and how we do these joins is when we say left join, it uses this word on. So where it's going to join them is where these conditions are met. So after on, we're going to provide some conditions where bank will match up to temp. So the first one we're going to do is the unique identifier we have for each company, where the GV key in the first data frame is equal to the GV key in the second data frame. So we want to make sure that the bankruptcy data that's joined on is for the same company. And so this allows us to link other conditions that we're going to join by. And this one we're going to try and join where the bankruptcy date happens after the fiscal year ends up to a little more than a year after that fiscal year. So we could change that to be just the next fiscal year. We could change it to be in the next 3 years. We could mess around with that some to try and, depending on what we want to predict, but I just chose like the next year to year and a half as a way to predict if a company is going to go bankrupt during that time. So we're going to say where the bankruptcy beginning date, so when you first enter bankruptcy or the company first enters bankruptcy, so that's from the B data frame. So B dot this gives the data frame and the column. So this is similar to when we're using our language where we say data frame $ column. Here it is data frame dot column. The beginning of the bankruptcy time has to be between, now this is over to the temp data frame, and it says the end of the fiscal year, that's data date. So where this bankruptcy happened between the fiscal year end and the fiscal year end plus 450 days. So it's saying sometime between the fiscal year end and 450 days after that. So then what that'll do is it'll push on any of this YBank variable. So yes, they had a bankruptcy, as long as it's for the same company and it happened in the year or so after that fiscal year end. So in other words, we can use the X variables we have to try and predict the subsequent bankruptcy. So when we go ahead and run this, we've created a new data frame, and we can look at that data frame as well. And we have all the same stuff we had before. Get to the end of the data frame, and it has this YBank variable. Well, notice a lot of these are NA. That is because a lot of these ones didn't go bankrupt. So we could keep looking, and there was one. So it was, maybe I was too fast passing it and you won't be able to see it. There we go. So this one had a 1. So this company in the year after this fiscal year end entered bankruptcy. So anytime that happened, then we're going to end up with a 1 in this data set. And by the way, just so you know, I created this data set to overlap with the same time period as the bankruptcy data set. Otherwise, it would not merge things on because we didn't have bankruptcy data, not because a company didn't go bankrupt. So these are from roughly the same time period. So if we have data that it says that they went bankrupt, it'll show up here. So notice what happened is we merged on from the temp data frame, we added from the bank data frame this yes, they went bankrupt variable. And again, it came from the same company, and the bankruptcy happened between the end of the fiscal year and and the following year plus some days. So that was the left join, but now that we have these NA variables, we need to predict zeros or ones, so we have to transform those missing ones into zeros. So I'll show you one way to do this here. So this is the column. So remember temp2, this is the data frame. $sign means the column for this yBank variable that we just added on to the data frame. And looking at this, the square brackets, this says wherever these conditions are met in this column over here. So this is for rows that meet these conditions. The rows that of the conditions that we're going to look at are is missing. So is.na is, it has an NA variable in that row. Then we're going to look at those, and the column we're going to look at for missing is this same data, or is this same column that we're looking at here. So in where the rows are NA for this column, look at this column and set all of those instances to 0. So this part's a little bit complicated, but let me go through the logic again. We're only looking at this column. Then the square brackets tell us the rows that we should look at. And the rows that we should look at, what we're going to use to determine that is to say, in this column where it is missing, look at those rows in this column. So if we used a different column here, it would still give us the rows to look at, and we could, for example, if this said temp2 F year, so where fiscal year, for example, met some conditions, we could do the same sort of thing. So again, where rows meet this condition here in the square brackets, we're going to alter the column that is given by this part, and what we're going to do is set them all equal to 0. So when we run that and go ahead and look at it again, notice all of the places that had NA are now 0. So now we've got zeros and ones in the data frame. We can use that to start modeling things. We're going to come up with some variables to predict bankruptcy. Some of these come from the slides and prior research that tried to come up with predictors for bankruptcy. I'm going to talk through these just quickly. So loss is if net income was less than 0, then that would give a true or false variable. As numeric makes it 0 or 1. So if it was net income less than 0, that will be equal to 1. I'm calling that loss. Current ratio is a ratio that tries to measure how liquid the company's assets are. So this is current assets divided by current assets plus current liabilities. There are other ways to measure this as well. I like this one because it's bounded between 0 and 1. The property, plant, and equipment as a percent of total assets gives a way to say how tangible are our assets, how much is in property or equipment or plants that can be used in a bankruptcy, for example, to liquidate. This debt coverage, so this is operating cash flows divided by debt long-term total. That's what DLTT is. Notice I'm adding 1 plus that. That's because some companies have 0 long-term debt, so then we would be dividing by 0, and that makes an infinite value, so that then this ratio won't work. Interest coverage is very similar. This is XINT is interest expense, so it's sort of the same idea as the debt coverage. Leverage is how much debt we have relative to assets or relative to equity. There are a bunch of different measures of leverage. So this is total liabilities divided by total assets, but again, some companies have 0 assets, so then I'm adding 1 to that, although there are very few that have that. And then this one is a measure of size, so I'm just doing the natural log of AT, which is total assets, and again, some are 0, so the natural log of 0, I don't want to have that in there, so I add 1 to that. So once I run all of this, I've got new variables to work with, and I can do a summary to look at the data and a few things to look at that are useful here. So first, our Y-bank variable, our percent of, or the indicator that says whether a company is bankrupt or not. The mean gives us the percent of companies that are bankrupt, so that is less than 1%. So rounded up, that's 1% of our observations have some bankruptcy. That's going to present some problems later that I'll talk about and show you. The min is 0, the max is 1. That's what it has to be because it's a 0-1 variable. The same thing happens with losses, 0 and 1. Well, here we have 50% of our observations have losses. That means we have a data frame that includes a lot of unusual companies because loss companies don't last, for a long time. So these are not large typical companies. Current ratio goes from 0 to 1. That's good. Property, plant, and equipment percentage of total assets goes from 0 to 1. Debt coverage, notice the numerator is cash flows, so it has very large negative cash flows, very large positive cash flows as a percent of debt. The reason we have these huge outliers is because some companies have very small debt, so we're dividing by something very small and using a numerator that is big, and so then we get these big outliers. So this variable is going to cause us some issues. This variable is going to cause us some issues. Notice leverage also has some very extreme observations here. And then log of total assets, it's reasonable here. So we're going to remove some missing values. So notice in property, plant, and equipment percentage, some didn't have the property, plant, and equipment variable. Some didn't have these current assets or current liabilities. So we're going to end up removing those. And that's when we do this missing part. Then for each year, we're going to remove these outliers of these variables that cause us some potential problems. So I'm going to go ahead and do that and keep only the columns that I'm interested in using here. So then once we do that, let's look again at what the mean Y-bank variable, so the percent of observations with bankruptcy, that removing those didn't change the percent too much, so it's still 7% of our observations, or 0.7%, so rounded up to 1% of our observations have bankruptcy. So I'm going to do a few things here. We're going to start to model these, and my default is I'm going to model this bankruptcy variable as a function of all of these variables that I've created. So I'm going to use a random sample, and I'm going to do it with set seed to make sure we get the same random sample. And we've seen this before, so now I've got two data sets, a training data set and a testing data set. Let's just check that we got a random sample that gives us a basic, that the bankruptcies sort of got randomly assigned. So in the training data set, we're still about rounded 1%, and in the testing data set, about 1%. So we got a random assignment of the bankruptcy observations. So once we have that, let's go ahead and try and create some models. You've seen these before, or at least this before. This is just LM, that's a linear model. When the Y variable is a 0-1 variable, a binary variable, that's called the linear probability model. So let's go ahead and look at that. So this creates the same output that you would have seen before. When we are doing a 0-1 variable, the R squared doesn't quite have the same meaning, so we're going to move away from that. But we can still interpret these significance values and t-statistics and these coefficients. We'll do that on one of the next ones, but these seem to line up with what prior research has found. Then we go ahead and predict. So we predict on the training data set. Remember, we called that fitted. So it's what the model says the bankruptcy should be. And we're going to look at that column that we just created. So a few things to notice. Notice that we have a negative probability. Well, we can't have a negative probability. It could be a 0 probability. So this linear probability model, because it isn't bounded to be between 0 and 1, it creates some probabilities that aren't really realistic probabilities. So because of that, people developed other probability models that we'll see in just a second. But the results and how these coefficients look end up being very similar. So people jump back and forth between which type of model they're going to use. And you'll see in the predictions they're fairly similar anyway. So okay, so we've got this negative probability that's a problem. Well, notice at the maximum, the highest probability that we give any observation of having bankruptcy is 0.08% or 8%. So an 8% probability of going bankrupt, well, what about those companies that are highly likely to go bankrupt? We've missed that. Well, the reason that is because the overall probability of going bankrupt in the data set is really small. Remember, we have less than 1% of our observations that go bankrupt. So the best bet, if you're going to predict for every company, and you want to get as much right as possible, the best bet is just to say no one's going bankrupt, and you'll get most of the observations right. So that creates some problems we'll see later. And if we wanted to then say, let's say even this maximum probability one, this one has 8% probability of going bankrupt, well, that's even a very low probability, so we're not too comfortable with this. It doesn't create something that says, yes, there's a high probability of going bankrupt. So the two most common probability models are this logistic model and this Probit model. Both of them can be done with this GLM, generalized linear models, and how the structure is the same as we do with LM. We just have to tell it what type of model it's coming from. So here, when we do family equals binomial, so remember a binomial is 0 or 1, so this will force it to use the logistic regression. If we use this other one over here, this binomial link equals Probit, that forces it to go away from the logistic into a Probit. And really the only difference is the underlying assumptions that generate that model, so not something to be overly concerned about. But we can run both of these and look at them as well. So we'll look at this one. Here's the logistic regression. You can pause and look back and see that these look fairly similar. These look fairly similar to what we had before. So okay, so far we look at the fitted part. One thing to notice here is when we predict with one of these other models, so some models require you to tell them what type of thing you're going to predict. So for the logistic regression, if you just predict, it's going to predict what is called what is the log version of this variable. So then it's not going to quite work the same way as the probability. So if we say type equals response, that says the thing it's going to predict is the response variable. So when we're doing this logistic and Probit, we're going to tell it to predict the response that we want to see, so it's interpretable. So we run that, and we can look and see what happened there. Well, we have some observations, so at least one observations we're predicting that it's a 73% probability that that company goes bankrupt. So now we have something that seems reasonable, although most of them, notice, are very low probabilities that we're going to predict that they go bankrupt. So maybe that is something that makes sense, and we're between 0 and 1, so at least by probabilities we can think about that in a reasonable way. Do the same thing with the Probit. And notice we're sort of similar. So now we have a 54% probability for at least one of those variables, and then most of them are really low, a little bit different from the logistic. So how do you choose? I don't know. So that's where we want to go and evaluate. And we're going to use what is called a confusion matrix. So a confusion matrix is what I showed before of when you're trying to get a variable right. I created a function so that we don't have to do it over and over again, but this function will create a data frame that will output whether the number of observations where, and let me go through the logic of this here, where what actually happened is equal to 1 and what is predicted is equal to 1. or what actually happened is equal to 1 and what was predicted is 0. So this one is incorrect prediction. This one is a correct prediction. Here we have the actual is equal to 0 and predicted is equal to 1. That's an incorrect prediction. And then the actual is equal to 0 and predicted is equal to 0. That's an accurate prediction. Okay, so when we run this, how I created the function is to make you input each column. So here, from the training data frame, input the YBank column, and from the training data frame, input the fitted variable from the model. And notice I just changed the number, so I used the linear probability model is fitted, the logistic regression is fitted 2, and the probit regression is fitted 3. So when I run this, this creates a data frame and outputs it from this function that I created. And here it tells me what was predicted was yes, you're bankrupt, or here, no, you went bankrupt, and then this is what actually happened. Actually, yes, you were bankrupt, and actually, no, you were bankrupt. Well, what happened here is that for the linear probability model, none were predicted to be equal to 1, and here's the problem that I wanted to talk about here. So here, what I did is, notice it says predicted is equal to 1 and predicted is equal to 1. Well, when we looked at this before, what happened was there were no 1s. All it was were probabilities. So those probabilities we have to turn into a prediction that is yes, it's bankrupt, or no, it's not bankrupt. So the way I did that is round the probabilities to 0 or 1. So when I run this, what you'll see is everything turned to 0s and 1s. And here for the linear probability model, everything is 0s, so nothing rounded up to 1. Here for the logistic regression, there was at least 1 in there, and if we go 0.00005, that's the percent of those that ended up in predicted being bankrupt, and similar for the probit regression. So now we can evaluate this with this function, and so let me show you each of these. So here we predicted nothing with bankruptcy. That means for those that were actually bankrupt, we have 413 that actually went bankrupt, and 55,825 that were not bankrupt, but we didn't get any bankruptcy prediction right. But what we did get right is a bunch that were not bankrupt. Well, here when we go to the logistic regression, it's a little bit different. So one of those that actually went bankrupt, we predicted that they would go bankrupt, so we got that right. Here, though, we predicted for 2 companies that they would go bankrupt, but they didn't go bankrupt. So we added a correct prediction for bankruptcy, but we added false prediction for bankruptcy here as well. So the question when we start dealing with this, what is correct and what is not in our predictions, is what do we care most about? Do we want to predict, and these are called type 1 and type 2 errors, not really important sort of thinking about knowing what that is, but the intuition and the important thing to think about is, do we want to make sure that when there is a bankruptcy we get it like we actually predicted it, but we're going to be wrong a lot of times, meaning we predict bankruptcy when bankruptcies don't actually happen? Or do we want to make sure we never cry wolf, meaning we don't predict it when it's not going to happen? So we face a trade-off here, and if we want to make sure we never call something bankrupt when it isn't, we would end up here in the linear probability model where we just say nothing is going to be bankrupt. If we're here with the logistic regression, we want to make sure we're saying things are bankrupt when they actually are bankrupt. Well, we got one right here, but we also added an error over here where we're calling something bankrupt when it isn't. So that you'll see this repeat as we go through these different models. For the probit regression, Notice we got one of them right when it actually was bankrupt, but we didn't falsely predict one to be bankrupt. So in terms of all of these models, we can't celebrate too much because we only got 1 out of 412. But if I were to choose one of these models, the Probit model seems to do best because you at least got something that was predicted to be bankrupt, and you didn't predict anything falsely to be bankrupt. Of course, we would like to do a lot better than this, so maybe this is the best we can do, but we can try some other things to see if we can improve on that. Okay, so I'm going to introduce some things that, not introduce, but I'm going to use the machine learning methods to try and predict. I'm going to introduce one new method. Other than that, we'll keep the same thing, and some of these last a long time, so you may not want to run all of them, or you may want to run them in parallel, or just walk away and let it run for a while. One of the things we need to do with the machine learning models is tell it that it's predicting a binary variable, and the way you can do it with this caret package is make your y variable a factor. So a factor, what it does is separate it so it has no numeric meaning. It just says there is a 1 and there is a 0, and I'm going to try and split those into separate buckets without even thinking about what it means. So in other words, if you had one that says blue and red, it would work on separating blue from red, but it wouldn't think one is higher than the other. So that's how you can force these machine learning models in caret to treat it as a binary outcome. So I'm creating this column ybank f or ybank factor. Once I have that, it'll run each of these models that we've already used with trying to classify the y variable rather than predict some actual number. If you had other things, for example, that you had classifications that were 0, 1, and 2, it would work the same thing. If you had red, blue, and green, same thing. Okay, so once we run this KNN regression, it shows sort of what it came up with. So we won't go through a lot of these things here, but we're going to go through and set them up. So now I'm calling this one predicted for. One of the things we have to do when we take it out, it's going to be a factor when we predict it. So when I run this here, it makes fitted for a factor because that's what we told it to predict. So then what we have to do then is change that factor into a number. So how we do that, we have to do it in 2 steps, otherwise it'll do something weird. So you have to turn it into a character, so that'll change it back to 0 and 1 but a character, and then make that 0, 1 numeric. So once we do that, then we'll have a factor back to a number. Of course, you wouldn't do that if it was 0 green and red or whatever. So we can look at this fitted for, and what comes out of it is it tells us, well, we have some that had a 1 prediction, and the mean was, the percent of those that had it was 0.001%. Go to this confusion matrix. So for the ones that we predicted, we got 5 where it actually was a bankruptcy, and we predicted it was a bankruptcy. So slightly better on getting it right there. Where it actually was not a bankruptcy, but we predicted it was, there was 1. So maybe we got slightly better when we use that. We can do the same thing with XGBoost. Let me run this, and looks sort of similar again. And what happened here? Well, we get 14 that we predicted were going to be bankrupt that actually went bankrupt, and now we've got 4 that we predicted were bankrupt and were not. So maybe getting 14 allows us to be okay with getting 4 wrong, but we're starting to at least get something here that, ideally we would like all of these to be predicted correctly, but we're kind of not there yet. So we do the same thing with the neural net model. You've seen that before too. And notice what it did is predict that none of them would be, this is like the linear model, none of them will be bankrupt. We get the same sort of thing. So that didn't help us very much. So what I wanted to do then is say, well, let's add a different type of neural net model. And what that does, it's called deep neural networks. And the specific one I'm using here is an autoencoder deep neural network model. You can, there are other ones too. There are lots of different types of neural network models, just like there are lots of different types of regression trees. So this one, though, will run a long time. So it's worth doing parallelized and letting it sit and run for a while. And it's, you know, this is, along with the XGBoost, this is one that is used commonly in competitions and seems to do pretty well. So let's look at what this turns out here. So notice, just like the other neural network model, didn't get us anywhere, right? So it still predicts 0 for everything. And so it misses all the bankruptcy ones, but it makes sure it gets the other ones right. So why is this happening? Why does this keep causing problems where we can't predict bankruptcies? Well, one of the reasons is that we don't have very many observations that are bankrupt. And so what it's trying to do is fit that for the entire data set, we're trying to minimize how many we get wrong. So this is like when we're doing the minimizing the squared errors, this is the same sort of idea. It's trying to say, let's get as much right as we can, and if there are lots of observations that aren't bankrupt, well then those are lots of ones that are going to matter a lot to make sure we get those right, and getting a few right that go bankrupt doesn't affect those measures as much. So the model doesn't want to allow us to start getting predictions wrong. Well, there are other ways we can deal with that. We can try and force it to do those predictions. One of the ways to force that is to do what is called oversampling. That means take the bankruptcy observations that you have and just repeat them in the data set a bunch. And so what that will do is think about the model fit things that it's trying to get to. So if you have lots of bankruptcy observations, now it forces it to say, I don't want to get those wrong either. So it forces a trade-off in terms of how it's going to fit the model. So let me show you how that works. So if we're going to oversample, what I did is take from the training data set and only keep observations where the bankruptcy is equal to 1. So run this. I'm calling that temp1. And we can look at that data frame. Notice all of these are bankrupt. Okay? So then what I'm going to do is just add that back to the training data set a lot of times. So you could, I don't know what the right number of times is, but I think a good starting point is try and add it back enough times that you're about even between bankrupt and non-bankrupt firms. So how I do that is rbind. Rbind is combine rows. So I'm taking the training data set, putting on the bottom of that training data set the temp1. So I'm repeating over and over and over this temp1. And so here, notice I'm taking training 2, and then where I've already added a bunch of these temp1s, doing it again, doing it again, doing it again. So when I add all of these on, we'll see the percent of the bankruptcy ones that I get. Notice I'm at 48% of our rows now have a bankruptcy observation. Notice I haven't, it's the same data, right? So the firms that go bankrupt are the same firms. Now we've just repeated it a lot, so we're forcing the model to make sure to not get the bankruptcies wrong. So I'm just going to show how this works with a couple of models. So if we do this with the linear probability model, remember the linear probability model predicted all zeros. So these t values are bigger. That's just because we've added more data to regression, and we'll go back and interpret some of these in just a little bit. So we're predicting, and notice here's the key part here. So I'm using this estimate that I just created, this model. I'm predicting on the training data set. So I'm not predicting on the one that has all of these bankruptcies added to it. It's the original training data set that only includes each bankruptcy once. But I'm going to use the model that was trained using all of those bankruptcies in it. And then when I fit it and I do a summary, notice now I've got, remember the linear probability model goes outside of 0 and 1, but now I have a bunch that have a prediction of being greater than 50%, one that is even over 100%, and some that are under 0%. So we still have that problem, but now the probabilities are much higher because our data set is composed of more bankruptcies when we estimate the model. So what does that do? So let's go ahead and look at that. So we have this fitted value that we would predict with. Notice we've got a lot of these ones that when it is a bankruptcy, 339 of these actually are bankrupt, and we call them bankrupt. We're only missing 74 that actually went bankrupt, and we didn't say they were bankrupt. But notice the trade-off here. Now we're calling a lot of those bankrupt that never went bankrupt. And so we've identified more bankruptcies, but the problem is we've cried wolf a bunch of times as well. So we have to make some trade-off here in saying, do we want to make sure we're definitely capturing bankruptcies when they do happen at the expense of getting a bunch of others wrong? Or in the other case where we had before, do we want to make sure when they're not going bankrupt, we don't falsely say they're going bankrupt? In that case, we might use a different model. So then let's do the same thing with this deep neural network model, just seeing if somehow that would help us. And what happens here? Well, now we're about even on the getting the actual bankruptcies right, and we are adding a bunch that we called bankrupt that are not bankrupt. And notice that's actually worse than this linear probability model where we're calling more bankrupt falsely and we're missing some that should be called bankrupt. So the deep neural network here didn't work, and the linear probability model works better when we're trying to use this sort of approach. Okay, so two things I want to do. Let's go through the out of sample. How did they work once we move to a new sample? It ends up being pretty similar to what we have seen already. So let's go ahead and look at that. And then I want to interpret one of the linear models. And so notice these will look similar to what we did before. I'm just putting them all together. So we have to round these ones because what comes out of them are probabilities. And then these ones we have to change back from a factor into a number. And this is a linear probability model again, and this is the deep neural network again. So run all of those. When it's doing the prediction, it takes a little while because some of these, and especially the KNN model, has to work a little while to do these predictions. And then it's going to create all of these confusion matrix for each of the things that we've predicted on the testing data set. So what's different here is we're using the testing data set instead of the training data set. So linear probability model, again, didn't predict any. Here, the logistic, we didn't predict any that actually were bankrupt, and we predicted 2 that were not bankrupt as bankrupt. So worse than the linear probability model, but both bad. The probit model, we predict none to be bankrupt, and that's what actually happened. The KNN model, we predicted none of the bankruptcy ones right, and we predicted 6 of the non-bankruptcy ones wrong. The XGBoost, we predicted 5 correctly that actually did go bankrupt. We incorrectly predicted 4 that didn't go bankrupt. The neural network nothing. We didn't predict anything, so that's, we're the same as all of these. Same thing with the deep neural network, anything. The oversampled versions of the linear probability model and the deep neural network model, very similar to the training data. So we get a lot of the ones that actually did go bankrupt for the linear probability model, but we also falsely predict a lot of times. And then same thing on the deep neural network. We get a bunch of them on both of these. So in the end, we don't have anything that we could say convincingly, yes, we have a fantastic prediction. But if our goal is to make sure we're predicting, and we want to make sure we never miss a bankruptcy, probably the best is the oversampled linear probability model. Of course, we didn't do the oversampling with the other models, so that's a possibility as well. And the other ones didn't seem to bias much. If the concern is, though, that we never falsely predict a bankruptcy when there is not one, then our best option is just to say none of them ever go bankrupt, right? So then we don't really have any that predict correctly a bankruptcy and don't mispredict a non-bankruptcy. So those are the trade-offs we have to make when we go to do this. So let's go back to one of the models just to try and do some interpretation here to see how that matches with prior research. So let's use the Probit. Probit, they're all linear probability model, logistic and Probit. They look very similar. To be a very precise interpretation, logistic is a little bit harder, but loosely you can do something very similar. So let's see what this means. So the y variable is 0, 1, and we're predicting the probability that a company is a 1. So this is positive. So if you have a loss, you have a higher probability of going bankrupt in the following year. If you have a higher current ratio, that means you have more current assets than current liabilities. You're less likely to go bankrupt. If you have higher property, plant, and equipment, you're more likely to go bankrupt, although that's not really significant. So maybe we say that one doesn't matter. For the debt coverage, if you have higher cash flows relative to the amount of debt you have, you're more likely to go bankrupt. But if you have higher cash flows relative to interest expense, you're less likely to go bankrupt. Well, why do we have those two conflicting things? Well, most likely this is because these are highly correlated, and when you put in really highly correlated variables, they can go to opposite sides. So the one we would expect is higher cash flows relative to the debt or the interest you have are less likely to go bankrupt. Higher leverage, more likely to go bankrupt, seems logical. And if you're larger, you're more likely to go bankrupt. That seems counterintuitive. That could be related to the leverage being correlated with total assets, or these other things being correlated with it. Or it could be related to the data that we have where we have observations for bankruptcies. We only have larger company bankruptcies and not smaller company bankruptcies. So that would be something to figure out and decide if we have all of the right data here as well. All right, so we've introduced a lot of problems, new binary stuff to look at, and we'll go ahead and try that on the homework and see what else you can figure out.